Fundamental concept. Electron shells in atoms.
Absolutely. It's the underlying architecture, really, that shapes how all matter interacts.
Everything from the air we breathe to, well, the devices in our hands. Consider this your shortcut to getting a deeper handle on chemistry's core ideas.
Yeah, whether you're brushing up on the basics or, just curious.
Our goal in this deep dive is to look beyond those simple diagrams you might remember from school.
Right, and explore the more nuanced reality of electron shells. We want to clarify how these arrangements dictate element behavior.
And how atoms form bonds, basically creating the world around us.
Exactly.
It's also worth remembering, I think, that our current understanding didn't just appear overnight. It's been a journey.
Oh, definitely. A fascinating scientific journey from early models right up to the quantum mechanical view we use now.
So we'll touch on that evolution too, setting the stage. Okay, let's unpack this. At a really basic level, what are electron shells?
Well, essentially, an electron shell is a region of space around an atom's nucleus. It's where you have a high probability of finding electrons.
High probability. Okay, so not like a fixed track.
Precisely. While it's sometimes helpful initially to picture them as orbits, it's much more accurate to think of them as representing specific energy levels.
Energy levels, got it.
Think of them like zones, yeah. Zones where electrons with a particular amount of energy are most likely to hang out.
So instead of a definite path, it's more like a probability map for electrons at a certain energy.
You got it. A probability landscape.
And this arrangement has huge consequences for how atoms behave, right?
Absolutely huge. This configuration is foundational to an element's chemical properties. It governs, how atoms interact, how they form bonds.
Determines stability, too.
Yes, stability, and even where an element sits on the periodic table. Understanding electron shells is really the bedrock of atomic structure and, well, all of chemistry.
Incredible. So you mentioned early models. Let's step back for a second. What were the first ideas?
Well, a really pivotal moment was Niels Bohr's model back in 1913. He suggested electrons orbit the nucleus in fixed circular paths.
Kind of like planets around the sun. That's the usual analogy.
That's the one. But his big idea, the revolutionary part, was that these orbits corresponded to specific quantized energy levels. Electrons could only be in these allowed orbits.
Not in between.
Not in between, like steps on a staircase, you could say. You can be on step 1 or step 2, but not floating in the middle.
Okay, like discrete energy steps.
Exactly. And Bohr also proposed electrons could jump between these levels by absorbing or emitting specific amounts of energy, often as light. He labeled the shells K, L, M, N, or used numbers. N equals 1, 2, 3, 4.
K being the closest, lowest energy.
Correct. K, or N1, is closest to the nucleus, lowest energy. Now, this model worked brilliantly for hydrogen.
The simplest atom.
Right.
One proton, one electron.
Right. But it hit limitations with more complex multi-electron atoms. The math just didn't hold up, and the observed spectra were much more complicated than the model predicted.
So the real-world data didn't quite fit for bigger atoms. Makes sense. So how did we get beyond fixed orbits?
That came in the 1920s with the quantum mechanical model. This was a huge leap thanks to people like Schrödinger, Heisenberg, de Broglie.
Some big names in physics there.
Definitely. A key realization was wave-particle duality. Electrons aren't just particles, they act like waves too.
Right, that weird quantum thing.
It is weird, but it led to the concept of orbitals, not orbits. An orbital is a 3D region where there's a high probability of finding an electron with a specific energy.
So less like a planet's path, more like a cloud.
Exactly. A blurry cloud of probability. Where the cloud is denser, you're more likely to find the electron. These clouds are the orbitals.
So the focus shifted from where it is to where it's likely to be.
Precisely. And Heisenberg's uncertainty principle kind of formalized this. It says you fundamentally can't know both an electron's exact position and its exact momentum at the same time.
Which kills the idea of a neat, predictable orbit.
Completely. Instead, the Schrödinger equation gives us mathematical functions, wave functions, that describe the energy and the probability distribution. Basically, the shape and orientation of these orbitals. It refines the shell concept with this probabilistic view.
Okay, so shells are still energy levels, but within them, electrons live in these probability zones called orbitals. Let's dig into the principal energy levels. The shells themselves, a bit more. What defines them?
The main thing is the principal quantum number, n. As we said, n is a positive integer, 1, 2, 3, and so on.
Higher n means higher energy.
Higher n means higher energy level, yes. And electrons in those higher shells are, on average, farther from the nucleus.
And held less tightly, I assume.
Correct, less tightly bound.
So is there a limit to how many electrons can fit in each shell?
Yes. There's a theoretical maximum. It's given by the formula 2nn squared.
Okay.
So for the first shell, n1, that's 2 times 1 squared, just 2 electrons.
That's the K shell.
Right. For n2, the L shell, it's 2 times 2 squared, which is 8 electrons. Then n-genols, 2 times 3 squared is 18 electrons. And n4, the n shell, 2 times 4 squared is 32.
2, 8, 18, 32. Useful formula. But there's a catch about the outermost shell, isn't there? It doesn't always fill up to that maximum.
That's a crucial point, absolutely. While the formula gives the potential capacity, the outermost shell of an atom, its valence shell, very often holds no more than 8 electrons for stability.
The famous octet rule starting to emerge here.
Exactly. The first shell, N1, is the exception there. It's stable with just 2 electrons, like helium. This drive for a stable outer configuration, usually 8 or 2, is really what drives chemical bonding.
Okay, so principal levels are the main energy tiers. But you hinted that electrons within a tier aren't all identical in energy. That brings us to subshells.
Precisely. It's not quite that simple. Within each main shell, there are 1 or more subshells or sublevels. These give us a finer distinction in energy.
And these are defined by another quantum number.
Yes, the azimuthal or angular momentum quantum number, usually written as L. For any given shell n, L can have values from 0 up to n1.
Okay, so for n1, L can only be 0. For n2, L can be 0, 1. For n3, it's 0, 1, or 2.
You've got it.
And these L values have letters associated with them too, S, P, D, F.
They do. L0 is called an S subshell, L1 is P, L2 is D, and L3 is F.
Where do those letters come from? They seem a bit random.
They actually come from early spectroscopy. When scientists looked at the light emitted by atoms, they saw a different series of lines they described as sharp S, principal P, diffuse D, and fundamental F. These corresponded to transitions involving electrons in these different types of subshells.
Sharp, principal, diffuse, fundamental. That makes more sense now. Okay, so for the first few shells, what subshells do we have?
Right, so N1 only has L0, so just the one subshell. N2 has L0 and L1, so we have 2s and 2p subshells.
2 subshells in the second shell.
Yep. Then N3 has L0, 1, and 2. That gives us 3s, 3p, and 3 subshells.
3 subshells.
And N4 has LLs 0, 1, 2, and 3, so we get 4s, 4p, 4, and 4 subshells. And importantly, each subshell contains 1 or more of those orbitals we talked about.
Okay, and orbitals within the same subshell, they have the same energy.
In an isolated atom, yes, they're considered degenerate, meaning they have the same energy.
Right, so subshells add another layer of structure. Now, these orbitals, the actual probability clouds, they have specific shapes and orientations.
Exactly. That's where the third quantum number comes in, the magnetic quantum number, m. This defines the orbital's orientation in space.
Okay, another number. How does m relate to m?
For a given L, L can be any integer from ml through 0 up to plus L.
Okay. So if L0 and S subshell, L can only be 0.
Correct. Which means there's only one s orbital in any s subshell.
And what's its shape?
Spherical, like a ball. The probability of finding the electron just depends on how far you are from the nucleus, not which direction.
Simple enough. 1s, 2s, 3s are all spherical, just bigger.
Bigger, yes. And the higher ns orbitals also have what we call radial nodes, spherical shells within the orbital, where the probability of finding the electron drops to 0.
Interesting. Okay, what about p orbitals? That's L101.
Right, for L1, Ln can be -1, 0, or +1.
So 3 possible values for LU. That means 3 p orbitals.
Exactly, 3 p orbitals in any p subshell. And they aren't spherical, they have a sort of dumbbell shape.
Dumbbell.
Yeah, like 2 lobes on opposite sides of the nucleus, with a flat plane, a nodal plane, going through the nucleus where the electron won't be found.
And the 3 orbitals are oriented differently.
Yes, they lie along the x, y, and z axis. We call them px, pi, and psc. They're identical in shape and energy, just pointed in different directions.
Okay, 3 dumbbell shapes along the axis. Definitely more complex than the Bohr model. Then we get to d orbitals. That's L2.
Correct. For L2, L can be -2, -1, 0, +1, or +2.
5 values, so 5 d orbitals. What do they look like?
They get more complicated. 4 of them usually look like a kind of cloverleaf shape, oriented in different ways between or along the axis, like dx, dxc, ds, dxs.y.
Clover leaves.
Wow. And the 5th one, the dss orbital, looks different, again, more like a dumbbell along the z-axis with a sort of donut ring around the middle in this I-plane.
Okay, these are getting hard to picture. We first see these in N3, right? 3 orbitals.
That's right. No d orbitals in shells 1 or 2.
And then F orbitals, L3. I bet those are even wilder.
They are. For L3, n log goes from -3 to +3, so that's 7 f orbitals. And yes, their shapes are very intricate, multi-lobe structures, quite difficult to describe simply. They start appearing at the N4 level, the 4f orbitals.
Okay, so the shapes get progressively more complex as L increases.
Hmm.
Shells, subshells, S, P, D, F, with specific shapes, and orbitals, L, null, defining spatial orientation. Is that all the quantum numbers we need for an electron?
Almost. There's one more intrinsic property of the electron itself, its spin.
Ah, right, spin, up or down.
Exactly. It's described by the spin quantum number, mers. It's also quantized and can only have 2 values, +12, which we often call spin up, and -12, spin down.
And this spin is crucial because of the Pauli exclusion principle.
Precisely. The Pauli exclusion principle is absolutely fundamental. It states that no 2 electrons in the same atom can have the exact same set of all 4 quantum numbers, n, l, m, l, and m's.
All 4 have to be unique for each electron.
Well, at least one must be different.
Okay.
And the direct consequence of this is incredibly important. Any single orbital defined by n, l, and ml can hold a maximum of 2 electrons.
Only 2.
And if an orbital does contain 2 electrons, they must have opposite spins. One spin up, +12, one spin down, -12.
So each orbital is like a little box that fits 2 electrons, but only if they spin in opposite ways.
Okay.
Keeps them slightly apart, maybe.
That's a good way to think about it. It minimizes repulsion.
Okay, putting that together. If an S subshell has 1 orbital, it can hold.
2 electrons. 1 orbital by 2 electrons orbital.
AP subshell has 3 orbitals, so it holds.
6 electrons. 3 orbital by 2 electrons orbital.
AD subshell has 5 orbitals.
10 electrons, 5 by 2.
And an F subshell with 7 orbitals.
14 electrons, 7 by 2.
2, 6, 10, 14.
Got it.
So we have the structure, shells, subshells, orbitals, and the rules for capacity. Now, how do electrons actually fill these levels in a real atom? That's electron configuration, right?
Exactly. Electron configuration is just the description of how an atom's electrons are distributed among its atomic orbitals, which orbitals are filled, and how many electrons are in each.
And there are rules for filling them. They don't just go in randomly.
No, definitely not randomly. The main rule is the Aufbau principle. Aufbau is German for building up.
Building up principle. Okay.
It basically says electrons fill the lowest available energy levels first before moving up to higher energy levels, like filling a bucket from the bottom.
Start low, go high.
Yeah.
Seems logical. Is there a set order for the energy levels? Because it's not always just 1, then 2, then 3.
Right. It's not strictly by the principal quantum number and alone. The general order is usually shown with a diagonal diagram, but it goes 1s, then 2s, then 2p, then 3s, and 3p.
Okay.
Then comes 4s, then 3rd, then 4p, then 5s, then 4, and so on.
Ah, there's that 4s before 3rd jump we talked about earlier. Why does that happen again?
It comes down to the subtle interplay of n and l. There's a rule called the n plus l rule. Orbitals with a lower sum of n plus l fill first.
Okay, let's try that. For 4s, n plus 3rd, L0, so n plus L4. For 3, n plus 3, L2, so n plus L5.
Exactly. Since 4 is less than 5, 4s fills before 3rd.
What if n plus L is the same? Like 3p, n plus L1, n plus L4, and 4s, n 4, L0, n plus L4.
Good question. If n plus l is the same, the orbital with the lower n fills first, so 3p fills before 4s.
Got it. So that n plus L rule, combined with the lower n tiebreaker, gives us the filling order.
That's the general guide, yes. It relates back to that idea of penetration we touched on. Orbitals penetrate closer to the nucleus, feel a bit more pull, and end up slightly lower in energy than you might expect just based on n.
Right, the penetration effect nudges 4s below 3 in energy. Okay, what about filling orbitals within the same subshell? Like the 3p orbitals, which have the same energy. How do electrons spread out there?
Ah, that's governed by Hund's rule. Hund's rule of maximum multiplicity.
Sounds important.
It is. It says that when you're filling degenerate orbitals, orbitals of equal energy electrons will fill each orbital singly first, with parallel spins, all spin up for example, before any orbital gets a second electron with the opposite spin.
So spread them out before doubling up.
Exactly. Think of seats on a bus. People take an empty double seat before sitting next to someone, and Hund's rule adds that they all prefer to face the same direction, parallel spins, initially.
Why? Is that more stable?
Yes, it minimizes the repulsion between electrons, leading to a lower energy, more stable configuration.
Can you give an example?
Sure. Take nitrogen. It has 7 electrons. Its configuration is 1 succo, then 2 electrons. That's 4 electrons used up.
Leaving 3 electrons for the 2p subshell.
Right. The 2p subshell has 3 orbitals, px by pz. According to Hund's rule, those 3 electrons will go 1 into each orbital, all with the same spin. So 2px, 2pi, 2p...
Not 2bx, 2p.
No. Spread them out first. 1 sucker, 2p, xpx, 2px, 2p eqp.
Okay. And of course, Pauli still applies max 2 per orbital, opposite spins if paired. Can we run through a few more examples of configurations just to see the pattern?
Sure. Hydrogen, 1 electron. 1 asleep. Helium, 2 electrons. 1 asleep, it fills the first shell.
Stable duet?
Yep. Lithium, 3 electrons. 1 asogan starts 2 acisses. Starts the second shell. Carbon, 6 electrons. 1 aciso, 2 acisses, 2po. The 2 electrons will be in separate orbitals according to Hund's rule.
Okay. Neon, that's a noble gas.
Neon, 10 electrons. 1 7 seconds, 2po. That fills the N and 2 shell completely, 2s and 2p. Very stable octet.
Right. Sodium, 11 electrons.
It's 1 aceton and 7 acetate, 2po, 3 acisses. Or, using shorthand, we can represent the stable neon core as Ne, so sodium is just Neth 3p.
Ah, the noble gas shorthand. That's useful. Argon, 18 electrons.
That's Neth 3 aceton, 3po, or just R. It fills the 3s and 3p.
Potassium, 19 electrons.
That's R 4 7s. We start filling the N4 shell before the third.
And scandium, 21 electrons, first transition metal.
That would be R 4 set of 3 diazises. Now we start filling the third orbitals.
It's fascinating how the structure builds up. Now, are there exceptions, cases where this nice Aufbau-Hund's rule filling order breaks down?
Yes, there are some well-known exceptions, especially in the D block and F block elements.
Well, why do they happen?
It boils down to stability. There's an extra measure of stability associated with having a subshell that's exactly half-filled or completely filled.
Half-filled or completely filled D or F subshells are good.
Especially stable, yes. So sometimes an atom can achieve this lower energy state by deviating slightly from the standard filling order.
Like promoting an electron.
Kinda. Look at chromium, Cr, 24 electrons. Following the rules strictly, you'd predict R4 thousands 3R.
Okay, 4 electrons in the third.
But experimentally, we find chromium is actually R4 3OD.
It moved 1 electron from fourth to third. Why?
Because having a half-filled third subshell, 0, 1 electron in each of the 5 orbitals, is more stable than having the 4s filled and a partially filled 3O.
So the stability gain outweighs the energy cost of moving the electron.
Apparently so. Copper, the cup, 29 electrons, does something similar. You'd predict R4 Cera2 3D.
Nearly full subshell.
Right, but it's actually found to be R4 7 3AI.
It promotes an S electron to get a completely filled D subshell.
Diaka.
Exactly. That full D subshell provides extra stability. So yeah, half-filled and fully filled D and F subshells are particularly stable arrangements.
Good exceptions to keep in mind. Now, how does all this shells, subshells, configurations relate directly to the periodic table? You said earlier it's basically built on this structure.
It absolutely is. The periodic table is like a visual map of electron configurations.
Yeah.
The rows, the periods.
Horizontal rows.
They correspond to the highest principal energy level, N, that's occupied by electrons in that element.
So period 1, hydrogen helium, uses N1.
Yes. Period 2, lithium to neon, has its outermost electrons in the NO2 shell. Period 3, sodium to argon, uses NO3, and so on down the table. The period number tells you the highest shell being used.
Simple enough. What about the columns, the groups?
The groups, the vertical columns, are largely determined by the number of valence electrons.
Valence electrons, those are the outermost ones. Primarily, yes. Electrons in the highest principal energy level, because elements in the same group generally have the same number of valence electrons.
They behave similarly chemically.
Precisely. Similar valence electron configurations lead to similar chemical properties. That's why group 1 elements, alkali metals, are all reactive metals, and group 17, halogens, are reactive nonmetals.
And those blocks in the table, SPDF.
They directly map to which subshell is being filled last as you build up the atoms according to the Aufbau principle.
Okay, so the S block on the left, groups 1 and 2.
Are elements where the last electron goes into an s orbital.
The P block on the right, groups 13, 18.
Last electron goes into a p orbital.
The D block in the middle,
Correct.
groups 3, 12, transition metals.
Those are filling the N1D subshell. Remember, third fills after 4s.
Right, the N1 rule for D block and the F block at the bottom. Lanthanides, actinides.
Yeah, they're filling the N2F subshell. For example, 4F fills after 6s.
Wow, so the table's layout is electron configuration made visible.
It really is an elegant reflection of quantum mechanics.
Let's nail down those valence electrons again. You said outermost N level. Are there any subtleties there?
Generally, it's the electrons in the highest in shell. So for sodium, Ne3 cell, it's just that 1,3 electron. For chlorine, Ne3 cecil 3Pa, it's the 2 plus 5 equals 7 electrons in the N3 shell.
Okay.
For transition metals, though, it gets a bit more complex. Because the N1d electrons are close in energy to the N's electrons and often participate in bonding, they're sometimes included as valence electrons, too.
Ah, so for something like iron, R4 Cyso 3 you might consider both the 4s and third electrons involved.
Yes, its chemistry involves those d electrons significantly, but the simplest definition focuses on the highest N.
And these valence electrons are the key to chemistry.
Absolutely pivotal. They're the electrons involved in forming chemical bonds, ionic or covalent. Atoms gain, lose, or share these valence electrons to achieve a more stable electron configuration.
Usually trying to get that stable noble gas configuration.
That's the driving force, yes. Often aiming for that octet 8 valence electrons, N6Np.
Or a duet for hydrogen and helium.
Or a duet, exactly. This tendency is captured by the octet rule.
And the number of valence electrons dictates reactivity.
Largely, yes. It determines how readily an atom gains or loses electrons, what kind of ions it forms, its typical oxidation states.
Like group 1, having 1 valence electron, easily lost to form +1 ions.
Yep. Group 2 has 2 valence electrons, forms +2 ions. Group 17, the halogens, have 7 valence electrons, tend to gain 1 to form -1 ions.
Then group 18, noble gases, have 8, or 2 for helium.
Making them very stable and generally unreactive. Their full outer shell is the goal for many other elements.
It all ties together. Okay, one more layer here. In atoms with lots of electrons, the outer ones don't feel the full pull of the nucleus, do they? Because of the inner electrons. Shielding.
That's a very important effect, yes. Electron shielding or screening. The electrons in the inner shells, the core electrons, essentially get between the nucleus and the outer valence electrons.
Like a screen, blocking some of the attraction.
Exactly. These core electrons have negative charge, so they repel the outer electrons, partially canceling out the positive attraction from the nucleus.
So the outer electrons feel a weaker pull than you'd expect just from the number of protons.
Correct. The net positive charge that an outer electron actually experiences is called the effective nuclear charge. We often write it as Zeph.
Zeph, is there a way to estimate it?
A simple way is Zeph is approximately the actual nuclear charge, Z, the atomic number, minus some screening constant S, representing the shielding by the core electrons. So Zeph as ZS.
And this Zeph affects atomic property.
Hugely. A higher Zeph means the nucleus pulls more strongly on the valence electrons.
Pulling them closer. Smaller atom.
Yes, higher Zeph generally leads to a smaller atomic radius.
Harder to remove an electron.
Right. Higher ionization energy. It takes more energy to pull that electron away if it's feeling a stronger effective pull.
And stronger pull on electrons in a bond.
Also, yes, higher electronegativity. So Zeph explains a lot of the trends we see across the periodic table. As you go across a period, Z increases, shielding doesn't increase quite as much, so Zeph increases.
Causing atoms to get smaller, ionization energy to go up, electronegativity to increase. Those key periodic trends.
That's the connection.
And you mentioned penetration earlier. S electrons getting closer to the nucleus than P or D electrons in the same shell. Does that affect the Zeph they experience?
It certainly does. Because S electrons penetrate closer to the nucleus, they are less shielded by the inner electrons compared to P electrons in the same shell.
So S electrons feel a higher Zeph than P electrons of the same N.
Slightly higher, yes. And P electrons penetrate more than D electrons, so they feel a higher Zeph than D electrons in the same shell, and so on. SPDF in terms of penetration, and the Zeph they experience within a given shell.
And that's the underlying reason why 4s fills before third. The 4th electron penetrates better, feels a higher Zeph for its energy level, making it slightly lower in energy.
That's a key part of the explanation, yes. It's this complex balance of principal energy level N, shielding by inner electrons, and the different penetration abilities of S, P, D, and F orbitals that dictates the final energy ordering and filling sequence.
Wow. It's intricate but beautifully logical when you put all the pieces together. This has been a fantastic deep dive. So just to wrap up, what are the absolute core takeaways about electron shells?
I'd say One, there are quantized energy levels where electrons are likely found. Two, their arrangement, the electron configuration, is governed by quantum rules like Pauli exclusion and Hund's rule, following the Aufbau principle generally. Three, this configuration dictates chemical behavior and periodic table position. And four, our understanding evolved from simple orbits to probabilistic
And
orbitals.
this isn't just abstract theory, right? It has real-world impact.
Absolutely. Understanding electron shells is crucial for everything from interpreting spectra to designing new drugs and materials. Even explaining why fireworks have different colors, that's electrons jumping between energy levels. It lets us predict and, crucially, manipulate matter at the most fundamental level.
It really is profound. The unseen architecture controlling the seen world. Thank you. This was incredibly illuminating.
My pleasure. Always fascinating stuff.
And for you, the listener, maybe take a moment to think about how this seemingly abstract idea of electron shells really underpins every material, every reaction you encounter daily, and maybe ponder. How could digging even deeper into these fundamental principles unlock the next wave of scientific and technological progress? What might we build if we truly master this atomic architecture? That wraps up our deep dive for today. Join us next time for another exploration.